Okay, so in this video, we are going to discuss the first part of section 2.1 of Griffiths' book, third edition. And what is this about? In this second chapter, we are going to solve Schrödinger's equation. What for? To finally obtain the wave function. And what did we do in chapter 1? We introduced Schrödinger's equation. We talked about the wave function. We said that all the information about the system is contained in this function. We discussed how we use this function to obtain expectation values, position, momentum, and different quantities. But in all the problems that you solved, this wave function was given to you. We never obtained it. That's what we are going to do now in this chapter 2. Okay, so let's write Schrödinger's equation and discuss what we are going to do, how we are going to proceed to solve this equation. So this is an equation that is second order derivative in position that depends on a potential. So how are we going to do that? We are only going to solve cases, we are only going to consider cases where this potential, which in principle would depend on position and on time, we are going to assume we are only going to study the case where it does not depend on time. It only depends on position, independent of time. This will simplify our lives, as you will see. As you will see, that solution for the Schrödinger's equation, the wave function, which depends on position and time, can now be written, only in this situation, can now be written as a product of two functions, one that depends only on position and one that depends only on time. Okay, so you see this letter here is again psi, just as here, but here we have the small psi and this is the capital psi. Or if you prefer to say it properly in Greek, is psi. Okay, so we can do this separation of variables. It works very well, as you will see. The separation of variables in the case where the potential only depends on position. Well, let's go. Let's see how we are going to proceed. I'm going to use this wave function back in Schrödinger's equation, but I'm going to write it in this product form. All right, so then that equation will be now written like this. The derivative in time will not affect the function of x, right? So I'm going to take this out. And the derivative, which was partial, is now going to be an ordinary derivative acting on the function that only depends on time. On the right side, we have now the derivative in position. So I'm going to take out the part that depends only on time, and I will have this ordinary derivative now only in that small psi. Okay, and we still have the potential. Remember, this potential only depends on x. Huh? And we have the product, little psi and phi. Okay, now what can we do with this? How is this going to help us? I'm going to now divide this equation. So I'm going to divide this equation by the whole wave function. So I'm going to divide by the product, which is the whole wave function. And what happens now? You see that we can now simplify certain terms. For example, we can simplify the psi here. On the right side, we can simplify the phi, and here we can simplify all of them. So you see that now here on the left side, there is nothing about position anymore. We only have time. So this function is only a function of time. On the right side, you see that we eliminated everything that depended on time because the dependence on time was in time. So on the right side, we only have x. So a function of time cannot be equal to a function of x. The only way for the right side to be equal to the right side is that the left and the right be a constant. which we are going to call E. Okay? So this is how our life simplifies, because look at that. Now we'll have two separated equations. One, which is this one here. Let's write this equation. We have this first order derivative in time equals to energy. Okay? On the right side, what do we get? We have now this equation here. Everything here only depends on x, as you can see. Okay, so we use the left side to obtain the function that depends only on time. And we use the right side to obtain the function that depends only on x. We combine the two, and we are happy because then we have the whole wave function. Okay, very good. So how can we now solve these two equations? Let's start with the left side, this equation that depends only on time. Let's rewrite it. Let me pass everything that does not belong to the derivative. Let's pass it to the right side. So we have here the derivative, left on the left side. And then what we have on the right, the energy, the function. We have that h bar. We have I in the denominator, but I'm going to pass it to the numerator with a negative sign. Okay? And the question now is, how do we solve this equation? This is a very simple equation. The derivative gives us back the function, some constants. So the only solution for that, which is a very simple one, is an exponential. So we have exponential 2 minus I e h bar. So these are all that part of that constant, t. Yeah. If you are not very convinced about this, you can do the derivative of this function that I just wrote and see that it will satisfy that equation. Or if you want to remember things that you probably saw in a math course, you could rewrite that equation like this. Pass the p to the left, have the constant and the dt on the right, do an integral of this. Here we have the ln of phi minus I e h bar and t. And what is this going to give us? That exponential that I wrote to you above. Okay? Now, usually what we add to this solution is a constant that will be telling us what happens to this function at time 0. But I'm not going to add this constant there. You know what? Because we know that this wave function has to be normalized. So we have this normalization constant that will show up there to guarantee normalization. And we can do this job, guarantee normalization, through this guy here. Okay, so I'm just going to keep this function of time like this without that constant. Okay, so this is the left side. We got this part. How about then the right side? Let me rewrite that equation that we have there. And what we are going to do, I'm going to multiply that whole equation by psi. So I take that psi out of the denominator. Okay, so this equation will become minus h bar over 2m, the derivative, second order. Since I multiply everything by psi, there is a psi now here, and there is a psi there. This is the equation that we need to solve to obtain the psi of x. Well, how can we do that? This is going to be the main point of this whole chapter 2. To solve this equation, we need to know what is this potential. And we are going to be working with several different potentials that allow us to solve this equation analytically. Okay, now this equation is very important. This is the time independent Schrödinger's equation. okay? And will be the subject of this chapter over and over again. We will be solving this equation, okay? So this is the end of this first part. Watch the next video for the second part, for the continuation.